Good morning, and thanks for coming to my virtual talk. Today we're going to be talking about the machine learning and computer vision challenges and opportunities in computational behavioral phenotyping. This is a very exciting, relatively new topic, and I hope after this short talk we will also get you very excited about the opportunities, both intellectual opportunities as a challenge and also the potential contributions to humanity. Before we go forward, let me just disclose my support consulting and gifts. And before we go even further, let's just hear from parents what they have to say. After all, our clients are the parents and the children with autism.
Grayson was our first child.
We thought maybe something was a little bit off pretty early.
We were told the wait lists for diagnosis with autism are really long, and I think they've only gotten worse from friends that I've talked to now.
The computer can see things that the human eye simply can't see. Well, when I first started doing autism research, the average waiting time for a parent who's worried that their baby or child might have autism is about a year. And so the challenge was, how do we come up with an app to be able to detect those early symptoms of autism, such as not making eye contact, not having normal facial expressions in a child's home? If a child is diagnosed at 18 to 24 months and provided 2 years of intervention, the average IQ gain is 17 points. So this has a huge impact on people's lives. And when I met Guillermo Sapiro, and he showed me that we could do what I've been doing in the clinic using a computer, that was an amazing moment for me.
So I've been doing computer vision and machine learning basically all my life. Using computer vision and machine learning, we wanted to see if we could help create an automatic analysis of autism and autism spectrum disorder.
Guillermo can use computer vision analysis to assess things like facial expression and attention. And so we built a set of movies that elicit these behaviors. And then we can show these on either a smartphone or a smart tablet and use the camera in the device to measure the child's response.
Data gets sent out from the phone to the cloud, and then we would be able to analyze that data, run it through our algorithms to produce our estimates of where the person is looking at. Now that we have this tool, what we hope to do is combine the eye tracking data, the gaze data, along with the motion, and jointly see if they can help in the assessment of the risk of autism.
Families simply don't have access to the professionals that they need. The idea that we could use technology to increase access, that's just a wonderful thought to me.
Every minute, every hour that you're able to implement those strategies, that's helping your child learn that social development and learn it with you. And as a parent, that is really rewarding.
Yeah. I think that if we can do just a small thing to change one kid, I think I would go to sleep with a smile. So a big thanks to Scott Collins and his family. He's also a partner in this project, and he volunteered the time of his family to explain a bit of their personal experience. And it's very important for us to remember all the time, we're not doing this for us, we're doing this for them. And so this is not about just writing papers, although they come out, it's about really contributions. So just a brief outline. I'm going to basically describe the problem and the challenges. We're going to describe the framework that we've been approaching and give you some examples and also tell you how this is inspiring new computer vision and machine learning. And then we're going to conclude. One of the things I always want to remind people is that we're not here to replace experts. We're here to assist experts, and it's going to be very clear when we move forward with the slides. So what's the challenge? The main challenge is about 1 every 9 every 10 children have a developmental disorder that impedes their maximal performance. So we're not comparing them with others, we're comparing them with themselves. So if we were able to help them, they would be able to perform better and live happier lives. And it's about 1 every 10. So think about just a regular a classroom, a kindergarten, an elementary school classroom. It's about 2 in every classroom, 2 to 3. And that's something that we always experience in our personal life, in the life of our children, that we see about 2 or 3 that need some kind of help. We are going to be concentrating during this talk in autism spectrum disorder. And we know that today the CDC actually numbers are a bit stronger today, I mean a bit harder. But the accepted number is about 1 every 59 children have autism. When we look at, for example, numbers in Sahara Africa, there's about 500 million children, and some of the numbers talk about 50 specialists to deal with all these children, which is incredible. There is no way to scale that up. Even when we look at North Carolina, in North Carolina, about 70% of the counties do not have a specialist. So we're privileged. We live in the triangle that has a large number, about at least three major clinical medical research centers. But outside of this area, situation changes. And that's very common in most of places in the United States. So the basic idea is that for autism and developmental disorders in general, and also neurodegenerative disorders, as you're going to see, many of the tools can be applied there, and we're actually applying there as well. The key is to observe. So there's not like a blood test yet, or even an MRI test, or a brain test. So you have to observe the behavior, and that's very expensive, very time-consuming, and there is no way to scale this up. So this is not about applying to a foundation and getting some millions of dollars to train, a handful of additional doctors. There is absolutely no way with the current system to scale this to the actual needs. And the consequence of this is that on one hand, so we see children, and on one hand, we know today that we can diagnose autism at 18 months to 24 months, but we should be going towards, can we do something earlier at 6 months, 9 months, 12 months? Time is critical. Or can we monitor them either because they're under treatment or just see if something changes in their life? So that's where we should be going today. But instead of that, we are in the wrong direction. The average diagnosis in the United States is about 4.5 to 5 years old. So that's about 300% of their lifespan of the child. So this is kind of, you're supposed to be diagnosed with a very difficult disease like a heart problem or a cancer at 70, and you're actually diagnosed at 210. So this is what happens, about 300% of the lifespan. That's what's happening today. So we are in the wrong direction. The science that we know in top clinical practices is not being moved to the actual public outside of these top clinical practices. So what's a possible solution? A possible solution, and this is, I'm talking about autism and developmental disorders, but applies to almost everything that we can think about, basically, is to start moving outside of the hospital. So once again, we're not saying hospitals are irrelevant. We're just saying they don't need to do everything today, and they need to do much less. So they become freer to do the stuff that needs to be done in the hospital. So the idea is to move something to basically schools, to houses, to basically where the children are. So Target actually does blood pressure. Why shouldn't Target be also doing developmental disorder, automatic behavioral screening, not diagnosis, but just screening? So same as blood pressure, they don't give you a blood pressure medicine, they just give you numbers that can help your doctor into making a decision. And basically, kids spend a lot of time on bus stops, on on planes, on many, many areas that we are underutilizing. Basically, we are utilizing zero. So the idea is just, it's like Netflix that went to your home with videos. We should be going to where the children are with this type of screening tools. So what we have been working very hard with an outstanding team is basically what we call active closed loop digital behavioral phenotyping or computational behavioral phenotyping, where basically the child sits in front of a smartphone or a smart tablet that is eliciting certain behaviors that are very well studied and very well reported in the literature. Some of them are new, some of them are more older and more supported, as we're going to see some examples. Then the camera on the device is recording the behavior. We're applying computer vision to detect a lot of the features that we are observing. And we are basically applying machine learning to try to learn which one of the features for the child or in the community are becoming important. And then we close the loops. So we're being active. We're basically eliciting behavior. So this is very different than, for example, a seizure detector that needs to be passive. So here we elicit the behavior, we record it, we analyze, we do computer vision and machine learning. So let's just see an example of a child that is actually looking at one of the stimuli. So we're following everything that she's doing and everything that is happening in the face. We are also doing some basically behavior of the body. You see, she turned the head when there was a name calling, so she paid attention, she shifted attention, she disengaged from what she was doing, and then engaged back. And we're tracking everything that she's doing at a very high rate, basically 30 frames per second. For some experiments, now even frontal cameras do 120 frames per second. So we will know at every frame what's happening. Is the child looking, is not looking, is paying attention, not paying attention, is smiling, not smiling, where is the gaze at every single frame. Normally in the clinic, the time frame, the time scale is about seconds, 1 second, 2 seconds. We are on the 30 frames per second. So we are at least 30 times faster, sometimes 60, sometimes 120 times faster. So here are just a couple of examples. As you saw in the video, there was a name calling. So basically in the middle of the stimuli, a clinician, a parent, calls the child. And we are expecting a typically developing child to turn around and be curious about, why are you calling me? So we measure that head turning. We actually, in this particular study, we did it 3 times. And then you can see in the graph in the middle that basically virtually no child that is typically developing didn't turn at least once. And no child that has been diagnosed with autism turned it 3 times. So the two extremes are very important biomarkers. But we also started to look at what happened in the middle. Why sometimes a child that has been diagnosed with autism actually turns? Is there any difference in that turn? And if you look at the graph on the right, we see that yes, there is a fundamental difference in latency. Basically, children with autism takes them more time to turn to that name calling. And you see the two distributions, they're almost non-overlapping, and there is about a second difference in the average. So this is kind of the things that was very hard for clinicians to see in the clinic, but actually because the computer is doing frame by frame, it can be much more precise on the timing of the name calling and the response to name calling than a clinician in the room could have been, because they're doing a lot of things at once. So these clinicians are outstanding, but basically that's a very hard thing to do. Once again, I might repeat this a long time. This is just basically not to replace what the clinician is doing in the clinic, like ADOS, which is the standard test for diagnosis. It's just to augment it, maybe augment it with data that was collected at home even. Here is another example. We pay attention, we look at the child, the one that is moving right now, that is typically developing when the child is paying attention to a stimuli, and you see that this manages to maintain her posture On the right, what's playing right now is a child with autism that, although is paying attention, is having a much harder time, basically in layman terms, keeping the head fixed. Basically, is doing a lot of movement while paying attention. And by the way, this result and the previous result have been published. If you just Google search our names, you will find the publications from last year. So these are results that repeat things that we knew that they happen, discovers new things, and also shows the feasibility of these tools to basically provide additional information for clinicians. And of course, they become very universal because you can just distribute phones or tablets in clinics. You don't have to have your own. As I say, you can just put them in Target. So before I continue, I just want to make sure that you understand that this is not me. This is just an incredible large team, and this is just a subset, because if I prepare the slides tomorrow, there will be more people. So we're adding people, and people are moving to their new adventures. And my main partner is Jerry Dawson, that leads the autism clinic at Duke, and basically is the clinical partner on this. But a very large team of superb people that basically do all the work, and then I get all the credit because I get invited to give these kind of talks, but the credit goes to them. So let me just give you a couple of examples of, okay, we need to do this, but if you're sitting and you're a computer vision person, a machine learning, you say, okay, let's say I don't care about the actual contribution, I want to do new computer vision and machine learning. That never happens because students do care about contributions to humanity. But let me just tell you what are the challenges, some of the challenges for computer vision and machine learning. One is that things have to work all the time. There is no time for calibration and for repeating experiments. They have to work all the time. So if you look at all the stimuli that we are designing, we know that good gaze tools that you buy from Toby can get very accurate gaze. But if you're going to only use the camera on the phone, you can't do that all the time. You can't calibrate, you can't do any of that. So we design stimuli that are only left and right. And basically, we design gaze analysis tools that they need to be very robust, but they only need to distinguish if you're looking at the left or you're looking at the right. So here is the closed loop, where we smartly design the stimuli that will elicit the same type of behavior that you were expecting in the lab, having a Toby high-end gaze tracker. How do I design a new stimuli that will get me the same signal, but now I need to do gaze analysis with a camera on a phone? So we work on the design of the stimuli, and then we also work on the design of the computer vision to be able to robustly detect left, right, or maybe 4 regions, but not the millimeter accuracy that you might be able to get with professional devices. Similarly, normally the professional devices need some kind of a calibration to the user, and we actually work very hard not to need calibration. And the basic idea is that you can have the child watch regular movies and use tools from computer vision related to saliency and basically guess where the child is looking. So you pre-start with basically very fun movies that force the child to look at certain regions, and you use that as labels. So you plug that into standard machine learning, deep learning type of tools for gaze analysis, but now with the pre-calibration that was done completely transparent to the child. And then you get immediately improvements in accuracy, about 25%. So this is completely transparent. You don't tell the child, oh, you now need to calibrate, just sit quiet and sit fixed. We just make the child for a few seconds watch an interesting movie. And using saliency maps, we basically design an algorithm to improve and personalize gaze for that child. Let me now give you another example of a problem motivated by what we have been describing. We normally collect data on mobile devices, and they have good cameras, but it's not the same as you get in a lab setting. So the question is, how do we combine data, low quality data with high quality data at the training time and also testing time? How do we give confidence? How do we say, I can tell you as much about this data, but not more? And we see here examples. If I provide you a full face, you can tell everything about this person. But if I give you a blurry face, you might just be able to say, this is a person and not much more. If we get a very sharp image of a truck, you can say it's a vehicle, it's a truck, and maybe even the brand of the car. But if you get a blurry image, you might only be able to say it's a moving large object and no more than that. So we develop a technique based on the concatenation of UNet networks that basically addresses that. At the training time, every network is only modified depending on the quality of the data that you receive. So if you receive low quality data, you only modify the front end of the network. And the higher quality data you get, the more you modify of the network. At testing time, each one of the UNet subunits gives you a coarse result that becomes finer and finer with certain confidence. So you're able to say, okay, up to here, I believe the output of the network, but I don't believe the fine results later on. Here is many examples that you can see. When we have on the left the original image, we're very good at all levels of decisions, from the very coarse information to the very fine information. The images on the right are blurry and distorted, and you will see that we still do very good on the coarse level, but we tell you on the fine level not to trust the network. Instead of giving you a wrong answer, we say, this answer, I believe a lot, the coarse answer. This answer, the fine answer, I might be right, but I give you low confidence. So that combines that both at training, we can use multiple data qualities and at testing, and that's very important. We also look beyond particular things like emotions, and we actually look at individual points on the face, how they are changing. So is that the children typically developing are smiling more, or is that they're moving certain landmarks on the face more? So once again, we start from the challenges, asking new questions on computer vision, machine learning, and data analysis that weren't asked before. Let me just finalize with another one, which will concern everybody, and it's the issue of privacy. And the idea is that we are actually recording faces of children, and there is many technology aspects to deal with privacy, from doing the entire biomarker and risk assessment on the phone, so it never goes to the cloud, to actually going to the cloud, being protected. But there is also one way of how can I filter out your face in such a way that I can detect the biomarkers I want while protecting other things. So maybe I only need to track those points. And we actually develop tools that are based on tools from information theory that basically allow us to design filters on the faces in such a way that the information that we need go through, and the information that you want to keep private actually gets blocked. And this is slightly different than the standard privacy work, the outstanding work on differential privacy, because this is very individualized to the child or to the participant, to the basically the patient in the case that this is deployed. And basically, I need to extract some information about you, not about average. And that's what we have designed. So once again, and I'm citing some of the papers just to show you that, yes, we end up publishing in clinical literature, but we also publish in the computer vision and machine learning literature, because this super interesting new problem also brings us new challenges in computer vision and machine learning. So I hope I have shown to you that digital behavior phenotyping is needed because of the scalability. It's actually possible. I'll show you, and I just gave you one example, but we actually deploy apps to download from the App Store and other places. So this is possible, and the mobile health can give you basically these tools. So there is tons of opening questions. So for the machine learning and computer vision people, there is a natural contribution to humanity. There is no dispute here. And one of the things that I want to finish with is that if you look at the faces of the people that are involved in this project, it's an extremely diverse team. And I think it's because it's such an interesting problem that diversity comes natural to it. I want to conclude by wishing you a very happy anniversary, giving you thanks for the honor of presenting to all of you. Thank you very much. Stay safe.